In this video, we'll cover the problem bacon numbers. To get us started, we're going to dive into what the question is asking, then we'll kind of map through the solution and how it uses a BFS, and lastly, we'll see how to code it. So, to understand this question, there are a few moving parts. Your input is going to be an actor. For our example, I'm just using a person named Grace. Your output should be the bacon number of that actor. So the bacon number is defined as the minimum number of degrees of separation between an actor and Kevin Bacon. So Kevin Bacon is an actor, and I have kind of modeled out what an example graph might look like for this question. So the node right here is the special node for Kevin Bacon, right? The bacon number is kind of defined based on Kevin Bacon. So this is the important node. Now, I have only used one letter names for these nodes just so that it would be easier to draw. But in the actual question, you'll have like full names like Grace or something like that. So if you were given the G node as your input, which is Grace, you need to figure out what is the minimum number of degrees of separation between the G node and the KB node. So you could go from G to A, which is 1, from A to I, which is 2, from I to E, which is 3, and then go back to I, and then, so you could count that as 4 if you want, and then go from I to B, which is 5, and then B back to I, which is 6, and then I to KB, which is 7. So it is possible to get sort of 7 degrees of separation between the G node and the KB node. But that's not what the question is asking. The bacon number is the minimum number of degrees of separation. So to get that, we would go from G to A, which is 1, A to I, which is 2, and then I to KB, which is 3. So the output for the G node for Grace is going to be 3, because the minimum number of degrees of separation between the G node and the KB node is 3. So you can imagine, if you were given Kevin Bacon as an input, you would get 0. If you were given I, C, or F as an input, you would get 1, and it kind of expands outwards using that pattern. Okay, so that covers what we're trying to do in this question. But there's another important note, which is that normally when we do these graph questions, we're given an array that contains a bunch of edges, and that's how our graph is stored. But in this question, your input is only a single string. So how do we actually know what the graph looks like? Well, we are given access to this special utility function. It's got a pretty long name, but it's called getActorsWhoHaveWorkedWith. And then you pass in the name as a string. So this function basically gives you the edges if you give it a node. As an example, if you were to pass in the A node, I can go ahead and mark it on the graph, this A node into the utility function getActorsWhoHaveWorkedWith, you're going to get all of the nodes or vertices of our graph that are directly connected to the A node. So you can see we've got D, G, H, and I as the nodes that we are receiving in our returned array. Okay, so that covers the idea of what the question is asking. We want the bacon number, and we have access to this special utility function. All right, so now let's talk about how we can actually solve this question. This, if you kind of figure out what the question is truly asking from a more algorithmic level, really what you're saying is what is the shortest path between two nodes. If we go back to our example with Grace, we determined that the optimal path that gives us this output of 3 here, right here, is going from G to A, which is 1, A to I, which is 2, and then I to KB, which is 3. If you notice what we're doing is we're just saying, what's the shortest path, right, to get from G to KB? And that makes sense, because if you model all of the actors out there in a graph, where the edges are saying who has worked together, really all the bacon number is the shortest path from the current actor to Kevin Bacon. It's almost like, well, it's the minimum number of degrees of separation, which is really the same thing, right? It's at minimum, how many edges do I need to traverse to get from this actor to Kevin Bacon? And once you think of it as this shortest path question, I think it becomes a lot more familiar and a lot easier to tackle using a BFS. Because we already know that generally when you have a shortest path question, a BFS is one of the first tools that you want to be considering. So really, that's all we need to do. We need to execute a standard BFS to figure out the length, actually I'll keep these, to figure out the length of the shortest path between our input node, in our case Grace or G, and the Kevin Bacon node. So let's go ahead and write out the pseudocode for how we would approach this. I'm not going to write out the full BFS pseudocode because we've seen that several times, so we'll focus on what's unique. So for here, let's just go ahead and start with, execute a BFS. I'll just write that, and we'll write some notes under it that are going to be what are the unique things about this BFS that we need to modify. So the very first thing is we have to handle this question, right? We don't have what we normally have, which is an array of edges. So the very first thing is to get neighbors of a node, we have to use our utility function. So we can write that. Use util function to get neighbors. And once we have the neighbors of a node, then this really just looks like a normal question with a BFS, at least in terms of the input format. We also know, and we've seen this before, that when we're doing the length of the shortest path between two nodes, we actually have to track what level each node is at when we put it into the queue. So normally our queue will just look something like this. It'll be an array and it'll have like A and then B and so on. But what we need to do that's a little bit unique is we need to store multiple pieces of information at each position. So we need to store, okay, the A node is what we have, but we also want to say the distance that we have traveled so far is going to be 1. And then for B, we want to say the distance we've traveled so far is 2. Because if you remember, once we get from the Grace node to the Kevin Bacon node, what we need to return is the Bacon number, the length of that path. And in order to have that, we have to be tracking every time we add an edge, like how many total edges have we traveled so far. So in our queue, we're going to store lengths as well. So let's go ahead and get rid of this sample queue, but we'll say store lengths in queue. And we've also seen this before, but it is something different from the standard BFS that we see all the time. So I want to go ahead and make a note of that. Okay, so we're doing a standard BFS. We are using our util function when we want to grab the neighbors of a particular node, and we need to store these lengths in a queue. One other note is that we have undirected edges here, so we want to make sure that we don't get in some sort of infinite loop where we go from G to A, and then A to G, and G to A, and A to G. And we can continue with that forever. So let's just say we're going to track visited nodes to avoid that infinite loop situation. Because, if we've already found that we can go from, let's say G to I, then we don't need to worry about, can we go from G to A to H to A to I or something like that. Like those kinds of strategies to get to I are not useful because we've already found the shortest path to get to I. So we don't have to consider those. So if we track visited nodes, that should allow us to execute a normal BFS with these 3 modifications to find the length of the shortest path between the input node and Kevin Bacon. The one other thing is that process node step that we always talk about, which is the question of what logic do I want to apply to each node. I'm going to write that here. So I'll just say PN is just going to be that process node step. What do we want to do? Well, we want to just check if the current node is Kevin Bacon. Because whenever we get to Kevin Bacon, we can go ahead and return our answer. So we'll say if node is KB, then we want to return our Bacon number, I guess we can call it. So we'll say return BN. I'll abbreviate that again, but BN is Bacon number, which is also the length of the shortest path between the input node and the Kevin Bacon node. All right, So this question is a little bit different because it's not just a matter of the BFS, but you sort of also need to parse the question and understand that it really is a shortest path question. And you need to know the format of the data because it's not the typical format. You kind of have to figure out how to manage that. But once you realize that it's the shortest path question, you can understand that it's BFS and kind of move forward from there. Okay, now, lastly, let's talk about the complexity of this solution. So we will start by defining our variables. I'll do it off to the side for the sake of space. So V is going to be the number of vertices in the graph. Even though that's not really an input, it still is something that we can count our complexity as depending on. And in our case, vertices represent actors. So this is also the number of actors in our graph. And E here is going to be the number of edges in our graph. And an edge is basically a relationship between two actors saying that they have worked together. So our time complexity is going to be O of V plus E, which we've seen before, and our space complexity is going to be O of V. We've seen this before, so I won't spend too long on this, but we're adding every node into the queue at some point in time, so that's O of V, and we're traversing all of the edges in the graph at some point in the worst case scenario, so we have to include the E. In terms of the space complexity, this visited portion right here, tracking all of the nodes we visited before, in the worst case could be the entire graph. And we also know that with certain special kinds of graphs, it's possible that we put the entire graph minus one node onto the queue at one point in time. So we get O of V for the worst case space complexity. Okay, that's all for the approach. So let's go ahead and switch over to the implementation. Now, let's see an example of how to solve this question in JavaScript. As usual, I've gotten us started with the example input and output, along with importing our queue here. Here we have the skeleton of our function, and we have a simple test based on the example that we've done before. Now, we have access to the utility function getActors who have worked with when we're solving this question. Obviously, my file isn't going to have access to that by default, so I set up a really small example that will allow us to test using the graph that we saw in the approach. This doesn't contain the entire graph. I literally just included what was necessary in order to make this example work, because I didn't want things to get too complicated, and that's not really the core of this question. But I have a simple graph here, and then I have this utility function defined. When you're attempting this question, you can just go ahead and use this utility function as if it works. We take care of how it works on the back end of InterviewAce. With that being said, let's go ahead and code through our solution. So we know that we're doing a standard BFS with a couple of modifications. So to get us started, let's create a new queue so we can do our BFS. And we know the first thing we want to do is add something onto our queue. Now remember, normally we just put the node itself into the queue. But we're also trying to get the length of the shortest path between two nodes with this question. So at each step with each node, we need to be also tracking how far is this node from wherever we started. In our case, that's going to be this actor right here. So I'm going to use an array that only contains two elements to track this information. So the first element of the array will be the name of the current actor, and the second element of the array will be the distance of that actor from the start actor. So if the input actor is Grace, obviously the distance of Grace, or from Grace to Grace, is just 0. She is Grace. So we just put 0 here. There are many ways to handle this. You don't have to use an array. You could create a class that has two properties with the actor name and their distance from the start, and create an instance of that class every time you want to add to the queue. You can also use JavaScript objects and just have two entries. One would be a key of, like, let's say name and a value of their name, and then a key of distance from start, and then a value of distance from start. There are many ways to do this, and it really comes down to personal preference. Any of them are fine. Okay, so we want to iterate so long as the queue has some elements in it. This is pretty standard. Now, we want to grab out our element from the queue, so we can just do something like queue.dequeue and grab out the node here, right? That normally would work, but in this question it's going to be a little different. because when you dequeue from the queue, you're going to get an array with 2 elements. It's totally fine to do it this way. You can do like node like that, and you can say actor name is going to be node at 0, and then you can say distance from start is going to be node at 1. That is a completely valid way to do this. I'm going to show one other way that you can do this using array destructuring in JavaScript if you prefer. You can do something like this and do it all in one line. You definitely don't have to do it this way though. Both methods are totally fine. I just want to show. So what this is going to say is q.dequeue is going to return an array, and it's saying take whatever is at index 0 and store it in actor name. Take whatever is at index 1 and store it in the variable called distance from start. So these two options are doing the exact same thing. I'll go ahead and go with this option that doesn't use destructuring, just in case anybody isn't familiar with it. The purpose of this is not the details of JavaScript. It's more of the algorithms behind it. But either approach is fine. So now we've handled the normal piece, which is just removing nodes from the queue. We know the next step is to process the node. We'll go ahead and come back to that afterwards, as we usually do. The next thing is we will need to add all of the neighbors of the current node or the current actor onto our queue. Normally, we get the neighbors by doing something like graph at our node, or in our case, it would be the actor name. But remember, the format of this question is different. So we want to use our utility function. So we'll say neighbors is going to be get actors who have worked with, and then you're going to pass in the actor name right here. Then we can just iterate over all of these neighbors and just add them onto the queue. So we'll just say, for now, let's just say q.enqueue to add them to the queue. We're going to add this current neighbor right here. Normally, we add a check here that's like, what if neighbors is undefined? We actually don't need to do that here because I've set it up so that we return an empty array in the event that the actor we pass in is not defined. So we don't have to worry about that. The other thing we mentioned in the approach was that we have to handle visited nodes, because otherwise we'll get in this infinite loop of going from A to B and B to A and A to B forever. So we shouldn't just add any node onto the queue. Instead, we only want to add unvisited nodes. So let's just create a visited set, or actually, I'll do it down here. We'll create a visited set, which is just going to contain all the nodes we've visited so far. And here we're going to say only add onto the queue if the current node is not in the visited set. Right now that's meaningless because the visited set is empty, but the idea is if we fill it correctly, then we should only be adding neighbors to the queue if they have not been visited, meaning they're not in the visited set. Okay, this covers the skeleton of the BFS. Pretty standard. We've seen this kind of stuff before, just slight modifications based on the format of this problem. Now, the interesting piece is what do we want to do for every single node in the graph? Well, we know that every node, whenever we visit it, should be added to the visited set. So let's start with that. Say visited.add, and we can just store actor names. You could do the entire node if you wanted to, but I think the actor name is much easier to do. Okay, so we've covered that. Now we're executing this traversal where we start at the input actor. We, store their distance from the start at 0, and then we just start iterating. We go level by level, and we say, all right, who has this person worked with, the input actor? Then you go through all of those people and see who have they worked with, and keep going and keep going. The main piece that's missing from our algorithm right now is how do we actually return the bacon number? Well, we know that you only complete this algorithm when you get from the input actor to Kevin Bacon. So another thing we want to do when we're processing each node is we want to say, have we found Kevin Bacon? And if we have, we can go ahead and mark or just return the value of distance from the start. So we can say if the actor name, to be clear, that's not the input actor. We're talking about the current actor name as we traverse. If that actor name is Kevin Bacon, let me make sure I spell it the same, capital K, capital B, with a space. Okay, great. And this is how it'll be on Interview Ace's backend too, so you want to handle it the same way, or spell it the same way. But if the actor name is Kevin Bacon, you want to return the distance from the start. And that should actually give you your answer. To be clear, the distance from the start is saying this actor's distance from the start. So for example, Grace, when Grace is our input, Grace's own distance from the start is 0. if you have the A node, which is directly connected to Grace, it'll have a value 1 greater than Grace. And I'm realizing we're actually missing something right now. But if it was done correctly, the A node would have a value of 1 because it takes 1 edge to get from Grace to that A node. Similarly, whatever value is in distance from start when we find Kevin Bacon is telling us the minimum number of degrees of separation from our input actor to Kevin Bacon, which is exactly the answer we want. But the one thing I messed up is that here I'm only adding neighbor onto the queue. But you can see, based on the way we defined our queue format on the top, we should be passing an array every time we enqueue into our queue. So we should go ahead and fix this. So we want to say new neighbor node is going to be an array that's going to contain the neighbor and it's going to contain the new distance. So what is the new distance? Well, let's say, I'm going to actually make this clear with an example. Let's say we have Grace, which goes to A, which goes to B. Let's say we are currently at A. And you know what? Let's add the levels for the ones we've done. So we started with Grace. That was 0. Then we went to A. You know what? Let's use square brackets so it's consistent with our array format. So we have A, which is 1. Now, when we're currently at the A node, we know that we traversed 1 edge to get from Grace to the A node. When we're adding the neighbors of A to the queue, we skip Grace because that's already been visited, but we're adding B. And the question becomes, what level should we add for B? Well, we know it took this many edges to get to the A node. In our case, that's 1. And it's going to take that many plus 1 extra edge to get to the B node. So really, when we add B onto the queue, the distance from the start for B should be the same thing that A had, but 1 greater. So we basically want to say, at this point, the level, or the distance from the start here, is going to be whatever the distance from the start of the current node is, plus 1. The current node is accessed right here, and we have its distance from the start. So we can just make sure that right here, we're passing distance from the start plus 1. So this is the distance of the current node, and if we add 1 to that, we get the distance for the neighbor node. Once that's done, we can just make sure that we're enqueuing the entire neighbor node, and that should cover everything for this algorithm. And I'll go ahead and clear out our example here because that's not part of the code. So to summarize, the way we're handling this is we're making sure that every element in our queue is actually an array containing an actor name along with their distance from our initial actor or our start actor. That way, as soon as we find an actor who's Kevin Bacon, we can just return the distance from start for Kevin Bacon, which tells us the minimum number of degrees of separation between the actor we were provided and Kevin Bacon. Down here we have our test, so let's go ahead and run this file to make sure that we didn't mess up. Let's make sure the terminal fits in the window, and if we run this, we get 3, which is the output that we expected. You can see that up here, and we saw that in the approach because we can go from G, which is Grace, to A, to I, which then can go directly to Kevin Bacon. So 1 takes us from G to A, number 2 takes us from A to I, number 3 takes us from I to Kevin Bacon, and we're done. All right, so let's briefly talk about the complexity of this solution. So we can define our variables first. We'll say V is the number of vertices, which is also equal to the number of actors in the graph. Again, that's not provided as an input. Really, there's very minimal dependence for the time complexity and space complexity on the input actor. And E is going to be the number of edges, which is a number of relationships between actors in the graph, which just means 2 actors who have worked together at any point in time. Okay, so our time complexity is O of V plus E, like a standard BFS, and our space complexity is O of V, like a standard BFS. We are adding every node to the queue at some point in time, at least in the worst case scenario, and we're traversing every edge in the graph at some point in time in the worst case scenario. Our visited set is taking O of V time because potentially every node or vertex in the graph could enter our set by the end, again, assuming the worst case scenario. And similarly, if we have the worst case scenario for the structure of our graph, then it's possible that all of the nodes in our graph, or vertices in our graph, minus one of them, are going to be on the queue at the exact same point in time. All right, that's all for this video, and I'll see you in the next one.